Hello again, grade 7s. In today's lesson, we are once again going to go through a variety of topics. This time we'll start by giving a general definition of energy, and then we'll look at conservation of energy in terms of the transformation of energy and transmission of energy. Then we're going to define thermal energy and do a calculation for the thermal energy of a substance. And then we'll finish the lesson off by providing a definition for heat and then talking about what direction heat transfers between two different objects. Learning outcome is to distinguish between heat and temperature. All right, so energy is a property or quality of an object that gives it the ability to do work and cause change. Now, I just want to clarify what it means to do work. To do work, you need to be able to apply a force to an object. And not only that, you have to be able to get the object to move. So if you can apply a force on an object and you can get it to move, then you are doing work. Energy is just the ability to do this. So if something has energy, then it has the ability to exert a force on an object or a substance and cause change in it. And typically the change we worry about is it can get the object to move or the substances to move around. Let's look at an example though. So my preferred sport, which is volleyball as opposed to golf. So in the process of serving volleyball, when you eat, we gain something called chemical potential energy. You can think of it as like a form of stored fuel. Potential energy is stored energy. So we have this stored fuel in us. Because we have this energy in us, this gives us the ability to do work. So what would this do? If I can do work, I can then apply force to the volleyball and it can cause change in it. I can get it to move from one spot to another. So that'd be an example of how stored energy can be utilized to do work and cause change. Energy is not a substance. And what I mean by this is that energy does not have mass and it does not take up space. If you took the volleyball and you put it on an electronic balance, you could get a digital readout of the volleyball in grams. Okay, so the volleyball is a substance because it has mass and it does take up space. Now, I have a 5-year-old son and he has an insane amount of energy. Like he's always like jumping around. In fact, while I film these videos, you can probably hear like these constant thuds in the background. That's from him running around and hopping around upstairs. I would say he has a lot of energy. The thing is, even though he has energy, I can't measure it directly. I can't take that energy and put it on top of an electronic balance and get a digital readout. There are other ways to determine like how much energy a substance has, but how much energy that an object has, but the energy itself is not a substance. It doesn't have mass, doesn't take up space, and you can't, like I said, put it on a balance and measure its mass because it doesn't have any. Quickly examine a principle called conservation of energy, although I believe this was discussed in a little bit of detail back in the interactions and ecosystems unit of study. What conservation of energy tells me is that under normal circumstances, energy cannot be created or destroyed. I say under normal circumstances because in some scenarios dealing with nuclear reactions, it is possible to do that, but we're not going to worry about that in grade 7 science. So you can't create energy from nothing and you can't just make it go away. But it can be transmitted from one object to another. And it can be transformed from one object to another. I just want to clarify what I mean by transmission. So for example, let's say that I had like object 1 and it's moving towards the right. And because it's moving, it has kinetic energy. And you have object 2 that's just sitting at rest. If it's sitting at rest, it doesn't have any kinetic energy at all. When object 1 hits object 2, well, maybe object 1 would stop. It might. I mean, it could keep moving as well. And then it causes object 2 to now move. So in terms of energy transmission, what I did is I took the kinetic energy of object 1 and I transmitted it. I put it over to object 2. I still have the same kind of energy though. I'm going from kinetic energy to kinetic energy. Just to have kinetic energy of object 1, then it gets transmitted to object 2. When it's moving, it then has kinetic energy. So that's what I mean by transmission. Transmission of one form of energy from an object to another. Transformation of energy means the energy actually undergoes a different kind of form. So the example, going back here, where when I eat food, I get chemical potential energy, and then I swing and strike a volleyball. Well, once I get the volleyball to move, then that's kinetic energy. So I've actually gone through a transformation from one form to another. The energy's gone from chemical potential energy to kinetic energy of the moving volleyball. But let's trace that example in a bit more detail. First things first, all energy comes from the sun in the form of, we call it light energy or radiant energy or electromagnetic radiation. We'll just use light energy as our description. Through photosynthesis, plants make use of that light energy, and then they can produce food. So what I have is light energy changes form from light to chemical potential energy. That is what I would call a transformation of energy. A transformation of energy goes from one form to a different form. Well, then let's say that we eat the plant. We eat the plant and then we go and play volleyball. So what I'm using chemical potential energy that's stored as a result of me eating the plant, and then it's being changed into another different form of kinetic energy, which is me swinging my arm to strike the volleyball. So once again, that's a transformation of energy because I've gone from chemical potential to kinetic energy. It's changed forms. Well, then let's say I throw the volleyball up in the air and I swing my arm and I actually hit the volleyball and get it to move. When my arm is moving, the arm has kinetic energy. When I strike the volleyball, the ball now has kinetic energy. So there hasn't been any transformation of the energy. I've just taken kinetic energy in one object, the arm, and put it over to another object, the volleyball. So we would call that a transmission of energy. So transmission is there's no change in form of the energy, just whatever energy I'm looking at, which in this example is kinetic energy, just gets transferred from one object to another one. The type of energy we're most interested in this unit of study is thermal energy and kinetic energy. Thermal energy is a measure of the total kinetic energy of the particles that make up a substance. When you look at that definition, it is almost identical to a definition of another term. If you take this definition and you replace the word total with average, then what definition would I have? A measure of the average kinetic energy of the particles that make up a substance is our quantitative definition of temperature. Now, even though there's only one word that distinguishes thermal energy from temperature, there is quite a bit of a difference in terms of determining the total kinetic energy of particles that make up a substance compared to the average. Well, let's go back to our substance that's made up of 5 particles. So we have the 20 joule particle, the 30 joule particle, 25 joule particle, 22 joules, and 28 joules. And in the last lesson, in the example problem, we did a calculation where we determined what the average kinetic energy of the particles was. And I believe the way we did that is we added all those numbers together. So we went 20 plus 30 plus 25 plus 22 plus 28, divided by the number of particles. And we got was our average kinetic energy. So our average EK was 25 joules. Thermal energy, on the other hand, is not a measure of the average kinetic energy of the particles. It's just a measure of the total. So to calculate the total kinetic energy of these particles, all we'd have to do is just add these numbers together. So if you do a calculation for this, my thermal energy would just be equal to my total kinetic energy of the particles that make up a substance. So that'd be equal to 20 joules plus 30 joules plus 25 joules plus 22 joules plus 28 joules. Therefore, your thermal energy would be 125 joules. So just note the difference here. Thermal energy is a measure of the total kinetic energy of all particles that make up a substance. So that'd be 125 joules. And then temperature is a measure of the average kinetic energy of particles that make up a substance. So if you want to get the average kinetic energy, you just take this one step further. Your average kinetic energy would be equal to your total kinetic energy, which is actually your thermal energy, divided by the number of particles that make up the substance. So again, just note the difference here between what it means to calculate a total compared to calculating an average. And thermal energy is all about the total kinetic energy of the particles that make up a substance. Now, let's say that I wanted to increase the thermal energy of a substance. There's two factors that thermal energy depends on, which means that there's essentially two things I could do to make the thermal energy of a substance larger. Okay, so look at my 5 particles, the 20, 30, 25, 22, 28 joules. Currently, my total kinetic energy and my thermal energy is 125 joules. What could you do that would actually increase the thermal energy? Well, one thing you could do is if you had more substance or more particles, let's say we had like an additional particle now, and this additional particle had a kinetic energy of 25 joules, then when I calculate the total kinetic energy or my thermal energy, we just add another term. And that would turn my thermal energy now into 150 joules. Therefore, thermal energy depends on the number of particles that make up a substance. The more particles you have, the greater the thermal energy. And that's because you'd be adding more of those individual kinetic energy values together. Typically, the more terms you add together, the larger the sum is going to be. Well, what else could we do? Let's say that we can't do that. Like we are just stuck with our substance. We can't add any more particles to the substance. What else could we do to increase the thermal energy of the substance? Well, what we could do is we could heat the substance up. If we heat a substance up, every individual particle moves faster. If every individual particle moves faster, their kinetic energy goes up. So let's say, for example, that if I heat a substance up, this particle is now moving with 25 joules of kinetic energy. This one's now moving with 35 joules of kinetic energy. This one, with the temperature increase, is now moving faster, 30 joules. This one's now moving with 27 joules of kinetic energy, and this one's now moving with 33 joules of kinetic energy. So I want to calculate it. If I go ahead and calculate my total kinetic energy now, this would be equal to, this number is now 25. This number would now be 35. This number would now be 30. This number would now be 27. And this number would now be 33. I believe when I calculate that, I just added 5 to every value. That should make it go up by another 25. So 25 plus 35 plus 30 plus 27 plus 33 would give me 150. So that's the second way that you could increase the thermal energy of a substance. You could heat the substance up, which would make every particle move with a greater kinetic energy. And then because they're all moving with greater kinetic energy, the total kinetic energy of the particles would go up. Therefore, the thermal energy of a substance also depends on the temperature. So those are my two primary factors. Thermal energy depends on the number of particles that make up your substance and the temperature of the substance. Heat. So once again, the name of the unit study is heat and temperature. We've given a definition of temperature, a good one now. So our good definition of temperature is the average kinetic energy of particles that make up a substance. But we also want to make provide a definition for heat. Heat's a word that's often not used correctly. Okay, here's my definition. Heat is the transfer of thermal energy from one object to another one. And this transfer of thermal energy occurs because these objects are at different temperatures. For example, let's say that we have two spheres. One sphere is at a temperature of 30 degrees Celsius, and one sphere is at a temperature of 60 degrees Celsius. When I touch these two spheres together, there is going to be a transfer of thermal energy from one object to the other. Now, what's going to be that direction of thermal energy transfer? Is it going to go from the hot sphere to the cold one, or from the cold one to the hot one? It turns out that heat, so heat is all about transferring thermal energy. Heat will always transfer from a hot to a cold object. And it will continue to transfer thermal energy until we reach a state of thermal equilibrium. Thermal equilibrium means that both my objects or substances would then be at the exact same temperature. So in this case here, the right sphere is at the hotter temperature and the left sphere is at the cooler one. Heat always goes from hot to cold. Always goes from a hot object to a cold object. Now, if you're wondering why that's the case, like why does thermal energy always go from hot to cold? Okay, well, let's say we have two objects. This one's hot, and this one here is cold. An object that is at a greater temperature would have particles that are moving a lot faster. So a substance at a hotter temperature or an object at a hotter temperature, I would expect the particles to be vibrating a lot more. So the particles in this substance would be vibrating much, much more. So what they would do is, it's kind of like a domino effect. Like the particles in this hot object would vibrate back and forth, and they would collide with the particles in the cold object. And that would cause the particles in the cold object to then start vibrating. So what I've done is I've transferred some of the energy from the hot object to the cold one as a result of particle collisions. Now, the opposite could not be true. Say, for example, you had a cold object and you had one that's hot. A cold object is barely going to vibrate at all. If it doesn't vibrate at all, how could it get the particles in the hot object to move? So that's why heat is always transferred from a hot to a cold object. Objects at a greater temperature have particles that are moving around a lot more. And if they're moving around a lot more, they're going to collide with particles in another substance and get them to move. All right, let's do an example where we look at this concept of thermal energy and heat transfer and thermal equilibrium. So we have two cases, case 1 and case 2. And what I want to do is, for each case, I want to determine which sphere has the greater thermal energy, identify the direction of thermal energy or heat transfer, and what would the temperature be of each sphere in thermal equilibrium. Okay, so Let's assume that these spheres are all made up of the same type of substance. So like maybe they're the same metal, like they're made up of, I don't know, copper or something like that. Okay, so part A for case 1. It says, which sphere is at the greater thermal energy? Now, thermal energy depends on 2 things. It depends on 1, the number of particles that make up the substance, and 2, the temperature of the substance. Okay, let's call this one sphere A. We'll call this one sphere B. And again, thermal energy depends on 2 things. Depends on the number of particles that make up the substance, and it depends on temperature. Those are my 2 factors. Well, both these spheres have the same temperature, so that can't be the deciding factor in which one's going to have the greater thermal energy. So then it comes down to, okay, which of these objects would have the greater number of particles? Well, the one that's bigger. The sphere that's bigger is the one on the left-hand side. So I'd say sphere A, because it is made up of more particles. So that's a deciding factor. B, what is the direction of thermal energy or heat transfer? Well, we know that heat always transfers from a hot to a cold object. So which one's the hotter object and which one's the colder object, sphere A or sphere B? Well, you can't really compare them. They're both at the exact same temperature. If you have 2 objects that are at the same temperature, then there is going to be no thermal energy transfer because they're already in thermal equilibrium. So I'll say no heat transfer. Since both spheres are at the same temperature. That's when heat transfer stops. Once 2 objects get to the same temperature, they're in thermal equilibrium, and then heat transfer stops. So if they're already at the same temperature, we've already reached thermal equilibrium, therefore no more energy transfer. C, what's the temperature of each sphere in thermal equilibrium? Well, they're already there. They're already in thermal equilibrium, therefore their equilibrium temperatures would each be 50 degrees Celsius. Okay, let's go to case 2 now. So in case 2, let's call this one sphere C. We'll call this one sphere D. Okay, which sphere has a greater thermal energy? Once again, thermal energy depends on these 2 factors, the number of particles that make up a substance and the temperature of the substance. Well, in this case, which of these spheres has the greater number of particles? Neither. They're the same size. So the deciding factor cannot possibly be the number of particles. The deciding factor would then be the temperature. Which sphere is at the greater temperature? Sphere C. So I could say sphere C has greater thermal energy because it is at the greater temperature. B, what's the direction of thermal energy transfer? Well, thermal energy is always transferred from the hot object or substance to the cold object. Which one's hotter? Sphere C. Therefore, we could say the direction of thermal energy transfer is from sphere C, which is, I'll put quote, unquote, the hot object, to sphere D, which is my cold object. Okay, C, what is the equilibrium temperature? Now, I really can only do this calculation if my two objects are made of the same material and they are the exact same size. If I can do that, the way I can figure out the equilibrium temperature is it's pretty much just a midpoint between the temperature values that you see. So how do we calculate a midpoint or an average? We can take these two numbers. So you go 50 degrees Celsius plus 26 degrees Celsius, divide them by 2. So that would give you 76 degrees Celsius divided by 2. Then your equilibrium temperature would be 38 degrees Celsius. So sphere C would go from a temperature of 50 to 38. Its temperature would decrease, and sphere D would have an increase in temperature from 26 to 38. Well, that's because it's gaining thermal energy. Energy is transferring from the 50 degrees Celsius one to the 26 degrees Celsius one. Now, once again, I just want to point out this thermal equilibrium calculation only works for like finding an average if the spheres have the same size. Like, for example, if like sphere 1 was 50 degrees Celsius and it was like humongous, and sphere 2 is like itty bitty, like super tiny, and had a temperature of 26 degrees Celsius, there's no way that when you contact these two that the equilibrium temperature is going to be 38. This one might decrease a little bit. Maybe it would change to like something like 49.9 degrees Celsius. Because it's so huge, it'd be difficult to change its temperature. As for this one, because it's so small, it would have a massive temperature increase. Maybe it would go all the way up to 49.9 degrees Celsius. The problem is there's no way for us to do that unless we have a more advanced mathematical model, which is not something we need to worry about at the grade 7 level. So we'll just look at when we have objects that are at the have the same size in terms of figuring out an equilibrium temperature. It didn't matter for case 1 that they were at different sizes because they were already at my equilibrium temperature. All right, so that's it for today's lesson on thermal energy. And you can complete the assignment that is called thermal energy. And I'll talk to you in the next lesson.